Hi everyone. Today we will discuss the crystal field theory. Crystal field theory is the one of the theory which explains the uh, metal ligand bonding, and in including of metal ligand bonding, it also describes the loss of degeneracy in metal valency d-orbitals. So here we are looking into the silent features of crystal field theory. The first statement is, as per crystal field theory, a complex is considered as central metal ion surrounded by multiple ligands with electric field. The first statement by which it describes the complex, where he says that the complex is a centrally situated metal ion where it's surrounded by the multiple ligands. For example, if we consider an metal ion surrounded by 6 ligands, where here there will be electrostatic interaction will takes place between metal and ligand to hold the metal by surrounded ligands will forms the complex of ml6 complex of ml6. This is how he describes the complex. In next statement, right, he says ligand nature. Here he considered that ligand as a point charge or point dipole. In crystal field theory, ligand is termed as point charge or point dipole. This is due to ligands are in anion, will be anion or neutral. When there is an anion, ligands are anion, which nothing but negatively charged species. For example, chloride is a ligand, right? Hydroxide is a ligand. So on, such anions can act as a ligand. So when they act as a ligand and having negative charged, fully negative charge on them, they can be considered as point charge, isn't it? They can be considered point charge or not. Having negative charge, we can consider it as a point charge, right? And thereafter, neutrals are considered as a point dipole, since neutral ligands, when we consider it, they may be ammonia, water, and so on, right? Here what happens with ammonia or water or something, some other neutral ligands, they carries number of non-bonding electron pairs, such as here ammonia. When we consider, in ammonia the nitrogen will have a non-bonding electron pair, where having non-bonding electron pair, and the electrons are negatively charged. This particular moiety, when polarizes, it will carry the partial negative charge, isn't it? Having non-bonding electron pairs and thus electrons are negatively charged, when the small t, when it is polarizes, it will surely carries the partial negative. So far, having these point of view in terms of neutral ligand, these are considered as a point dipoles. Point dipole. Neutral ligands are considered as point dipoles, and charged anions, anion ligands are considered as point charges. Okay. In third statement, what they describe that the metal to ligand bond is electrostatic bond or electrostatic interaction. The metal to ligand bond is electrostatic interaction. Why? Because metal we are considered as a positively charged anion, and ligand, as per the second statement, we said that the ligand is either it is negatively charged anion, or it is said as point charge, or it may be point dipole. So it may carry full charge, negative charge, or partial negative charge. Having bond between them, right, positively charged metal and negatively charged ligand, there will be attractive interaction will take place, right. This attractive interaction can be considered as electrostatic bond, right. Why electrostatic attraction will be takes place? Since there is the metal positive, ligand negative will, when they are coming to closer, right, there will be have attraction, isn't it? Since we know that the two different charges will have attractive interaction, two same charges will have repulsive interaction. Here metal is positive, ligand is negative, which nothing but both are in different metal to ligand different charges, so get attracted, and that could be described, the bond between, right, the bond between metal and ligand is described by electrostatic attraction, right. So coming to fourth statement, the metal to ligand bond is purely ionic, isn't it? By the last statement you can confirm that it is purely ionic, electrostatic, and there is an attractive bond between metal and ligand, nothing but it is ionic in nature. So the metal ligand bond is purely ionic and not covalent, right, it would not be covalent, right. So by the third statement is confirmed that it is ionic but not the covalent, right. So as the metal and ligand bond is not covalent, the orbital overlap between metal orbital and ligand orbitals may not take place, isn't it? As it is a simple ionic bond between a metal and ligand, there will not be any orbital overlap, isn't it? When there is an orbital overlap, the electron has to be shared between two sides. But here we are saying that the bonding is due to the positive negative interactions, purely ionic. When that is there, there will not be any electron sharing between metal to ligand as per crystal field theory. So with that, the fifth statement is concluded as there will not be any orbital overlap between metal orbitals to ligand orbitals. So with all the five statements, it is explaining the how far, how could be the metal to ligand bond is taking place in the complex. So in the sixth statement, it describes the loss of degeneracy of valency d orbitals in transitional metal complexes, right? That's how it could be is, let's see the sixth statement. He says that due to ligand approach towards metal ion, due to ligand approach towards metal ion, the valency d electrons in transitional metal complexes will get repulsions, right? How it could be takes place, let we see. We know that metal ion having multiple orbitals, right? Let's see, these are the metal orbitals, right? So when here the ligand is approaching towards the metal ion, what happens? The charge, the negative charge, partial negative charge or direct negative charge will get interaction with the valency electrons, right? Whatever the valency electrons are here in the d valency orbital, they will get in repulsive interaction with the charge of the ligand side, with the charge of the ligand side, and whatever it carrying the uh, non-bonding electrons, with these non-bonding electrons or charge of negative of ligand will get have repulsive interaction with ligand valency electrons, right? So with this repulsive interaction, what happens is that the d orbital, valency d orbital, will destabilizes, will get destabilizes, right? And when it destabilizes, so the degeneracy of d orbital will loss, will loss, right? So when there is an repulsive interaction is taking place, which making the destabilization of the complex, still to have existency of complex, right? Even having destabilizing factor, still the attractive interaction, the bonding between metal and ligand is taking place, nothing but this particular disturbance, this particular destabilization factor will be overcomes. How it could be overcomes is by losing the degeneracy of the valency d orbital of transitional metal complex. When it is loses the degeneracy of valency d orbital, then it would get be it would stabilizes and there will be bond it takes place, right? How we can come to know, right? This can be example within simple example, right? uh, think that uh, in a village there are two opposite persons, right? Two opposite persons, when they are coming together, what happens? As they are opposite persons, there will be quarreling, surely it takes place, right? So but still to have their existence in same village, what they have to do, they have to go far away from each other. When they go far away from each other, there will not be any disturbance between them. So there will be the village will be get stabilizes, there will not be any disturbances, right? Same similar concept here we can adapt, right? What happening here, the electrons, sorry, the when ligand is approaching, right, uh, the interaction between ligand negative charge and metal valency electrons are taking place. So here we have to be accommodate these disturbance, we have to accommodate in a manner that they should to be go far away, right? These quarreling persons should to be go far away, right? Here to get far away, what happens is that the valency orbital, whatever it is there, that get splitted into different energy levels, right? Nothing but that splitting of d valency d orbital is nothing but degeneracy. Okay, loss of degeneracy. So before going for that, we have to know the new terminology of degeneracy. What it means by degeneracy? It means existing as a group, right? Degeneracy is nothing but existing as a group, right? So here, right, we can example in multiple example here we can give for the degeneracy, right? We know that 1 dozen bananas, which nothing but what, 12 pieces, isn't it? 12 pieces of banana, right? Where dozen is the group of 12, right? That is how, right? That is how this dozen, it indicating the degeneracy of the 12 pieces of banana, right? Same similar to that, octa, a term of octa is indicating that 8 group, 8 items or 8 pieces or 8 things group it is, right? Similar to that hexa, which indicates the 6 group, like that. All these terms, whatever they are said, is here octa, hexa, dozen, all they are describing the degeneracy of something, right? So similar to that, right, similar to that, when we observe the degeneracy in valency d orbital, it having an 5 degeneracy. Here the chemistry term here we are involved, that is what degeneracy, which explains the group of the orbital. Here 5 group of orbital, d orbital is said as 5 degeneracy. We know that d orbitals are dxy, dyz, dzx, dx square minus y square and dz square. These put together, these 5 orbital put together, we will term as a d orbitals, right? These 5 d orbitals is termed as a 5 degenerated d orbital, right? This group of 5 degenerated d orbital, when ligands are approaching to have bond between metal and ligand to exist as a complex, there will be slight negative interactions are taking place. To get that negative overcome for the does negative factor, repulsive negative factor, the degeneracy, 5 degeneracy of d orbital get loses, nothing but these 5 orbitals will get separated in 2 groups or 3 groups or 4 groups, in multiple groups. Here they are in one group, na? They are existing as one group, but after this metal to ligand interaction in complex, thus 5 group will be get splits into different number of groups, right? This is nothing but loss of degeneracy, loss of degeneracy uh, in metal valency d orbitals of transistor metal complexes. One more time I will say that why it has to take place is when ligands are approaching towards the metal ion, the valency orbitals will have certain electron density. Thus electron density will surely have negative charge. Electrons nothing but negative charge, na? So they will carry certain negative charge, and approaching ligand we are termed as a negative dipole, point charge, right? Which are have negative charge, right? Negatively charged. So these negative interactions are surely a repulsive interaction, isn't it? Right. Similar charges, when they are getting closer, they will have repulsive interaction. Here such repulsive interaction will take place, right? So when there is repulsive interaction is taking place, and still having this repulsive interaction, that should to be the metal to ligand bond should takes place. To have metal to ligand bonding, this negative interaction should overcome. To overcome this thing, the d orbital will sacrifices their degeneracy, right? Valence d orbital will get loses their degeneracy, where the five degenerated d orbital will get splits into different groups of d orbitals, right? This is what happens, right? This particular splitting of d orbital will depends upon two factors, right? The two factors are depends upon two factors. One is d orbital d orbital's orientation about coordination axis. About coordination axis, we know that there are three coordination axes: x axis, y axis, z axis, right? So along those axes, with respect of those x y z axis, how does the d orbital lobes are oriented will be the factor which defines the splitting, right? And second factor from the ligand side, ligand approach ligands approach in metal complex, and number of ligands, right? These two factors, with respect of these two factors, there will be splitting will take place, right? So with these two factors, there are two statements we can give here, right? The statements are: the d orbital the d orbital's lobes oriented in ligand approach will get repulsive interaction and destabilizes. Therefore, increases energy, increases their energy, right? For example, metal having 4 ligands in x and y axis, in along x and y axis in a complex. If the 4 ligands are along the x-axis and y-axis, right, then what happens is that we know that if this is in metal middle, this is an x-axis, left to right we consider, every time we consider as x-axis, and front to back we will consider y-axis, right? Here, if along each x-axis and y-axis, if we have 4 ligands, this type of, if it is in complex, consider x square y square orbital, consider x square y square orbital, right? Here the statement is what? The orbital lobes which are along the ligands approach in a metal complex, they get repulsive interaction and get destabilizes. When they get destabilizes, they rises their energy, reaches to higher energy level, right? So here, for example, we consider that in a metal complex, 4 ligands around the metal or along the x and y axis, like this, right? There, if we consider one of d orbital, dx square minus y square, right? And thus dx square minus y square, we know that it's structured as 4 lobes are along the coordination axis, 2 along the x-axis, 2 along the y-axis. As per d orbital structures, it is clear that dx square minus y square will have the 2 lobes along the x-axis, 2 lobes along the y-axis. So with this particular orbital, at the point of here, when we incorporate same structure here, what happens? The dx square, metals dx square minus y square orbital, 2 lobes along the x-axis, 2 lobes along the y-axis, right? What happens? The negatively charged ligands and the electrons of dx square y square will get repulsive interaction, when they get repulsive interaction, what happens? This particular dx square minus y square will get destabilized and increases its energy, right? Increases its energy. So it never be anymore in the 5 group d orbital, dxy, dyz, dzx, and dx square minus y square, dz square. Here it cannot be there. In this situation, it rises its energy. Dx square minus y square will get reaches to the higher energy level, since it having a negative impact of ligand approach, right? So with this negative interaction, it get enhances its energy, right? So second statement, statement B, the d orbital lobes oriented in the d orbital lobes not oriented in ligand approach. Ligand approach will stabilizes and get lower or decreases their energy. Decreases their energy, right? Isn't it? They decreases their energy when the ligand approaches away from the certain d orbitals, right? Certain d orbitals, the ligand approaches away from the certain d orbitals, thus they never get interaction with the ligand negative charge or ligand electrons, right? So when there is no interaction between d orbital electron density and ligand electron density, d orbital electron charge and ligand electron charge, so there certainly no any negative interaction. When there is no negative interaction, that could be stabilizes, the orbital will be stabilizes, and that decreases their energy, right? They thus orbitals will get stabilizes and decreases their energy, will gets into lower energy level, right? Same the situation what we consider here, same the situation when we consider, but the orbital when we get different, when we take in different, here we consider the d xz orbital, xz orbital when we consider same metal ion having 4 ligands on x-axis 2, on y-axis 2, right? On x-axis 2, on y-axis 2, but the orbital is different, right? Here we consider that orbital is different, and here the orbital, and this is an x, this is an z. In such, if we take, it has a lobes in between of x and z, x and z. Looking here, it may be on plane, but actually when we assume this here, it would be different. Here we have the x-axis here, same x-axis here, but the uh, front and back axis what we consider here is y, here it is z. So same when we incorporate here, the z-axis is towards up and towards down. The z-axis is along the upward and along the downward, right? Such how this is the way it would be, right? This is the way the z-axis will be there, right? So now this is z-axis and this is x-axis. Now the lobe, how it could be? The lobe will be, the lobe will be here from the top right, in between of x-axis and y-axis, in between of y-axis and x-axis, top right here like this. The lobe dumbbell shape will be like this, right? And downward in between of z-axis and x-axis, z-axis and x-axis, downward it will be there, down left, down left, right? And same another lobe, right, in between of x-axis, sorry, z-axis and x-axis, in between of z-axis and x-axis, it will be top left like this, top left like this, right? And another fourth lobe will be z-axis, x-axis, downward right, downward right, right? Like that it would have the, right? Here the lobe of x z or zx orbital will be like this, above the right, its second lobe will be downward left, downward left. Same together, third lobe will be right here, above left, and its partner fourth lobe will be downward right, downward right, right? Actually the ligands are how, on paper all the 4 ligands along the x-axis and y-axis, nothing but on the paper, right? But whereas the dzx lobes above the plane, right? We are writing above the plane, right? So which nothing but there is no interaction between these lobe with the ligand charge. So when there is no interaction with the lobes of the particular dzx orbital and ligands, so they will not have any repulsive interaction, they will get stabilizes. When they get stabilizes, they get lower their energy, right? So here same in the situation of here, the dzx orbital will get lower its energy, right? Same the case we are observing, same the case of ligand approach. But when we consider different orbitals in the uh, d5 group of d orbital, they are having a different interaction. Like this, all the 5 orbitals of d may have different interaction with ligand approach. With this different approach of ligand, some orbital will get lower in energy, some will get higher in energy, where they will get splitting. This, when it is happening, lowering energy of some orbital, hiring energy of some orbital, which making that different group 5 group will never be exist. That will be splits into different groups of the orbital. This splitting of different groups of orbital of 5 degenerated d orbital is nothing but loss of degeneracy, splitting of d orbital. That how the crystal field explains the loss of degeneracy in d orbitals of transitional metal complexes, right? So this is the crystal field theory, where it describes the complex and complex bonding as ionic, and the loss of degeneracy in d orbitals of transitional metal complexes. So here I conclude the class. By the next class we will discuss the more. Okay, thank you.